The English sky erupted in green fire. Did the sun just turn night into day? It is 11 a.m. On September 1st, 1859, and a thin, hazy light spreads over the English countryside. In the modest garden of his Redhill home, amateur astronomer Richard Carrington lifts his modest refractor and watches a sudden, brilliant white flash erupt on the solar disk. The flash lasts only a few seconds, but its intensity is unlike any sunspot he has ever recorded. Seconds later, a jagged plume of light, what modern scientists recognize as a coronal mass ejection, streaks outward, vanishing beyond the solar limb. Almost simultaneously, another keen eye records the same flash. Richard Hodgson, an amateur astronomer living in England, notes the exact moment in his logbook, confirming that the sun has produced something far more violent than a routine flare. Neither man knows that their observations will become the first documented link between a solar eruption and a terrestrial magnetic disturbance. Hours later, the aurora begins its unprecedented display. Instead of the faint red curtains that occasionally grace high latitudes, a vivid tapestry of greens, purples, and scarlet ribbons sweeps across the sky, visible from the Arctic Circle down to the Mediterranean. In Paris, some observers later recalled the sky as a river of fire that turned night into day. In the Swiss Alps, shepherds herd their flocks beneath a glow that seems to set the mountains ablaze. Contemporary newspaper accounts from New York described the evening sky in similarly dramatic terms, as if the heavens themselves were aflame. Even in daylight, observers along the coasts notice a faint, lingering luminescence on the horizon, as if the sun itself had left a faint afterglow. The aurora is only the opening act. By early evening, telegraph stations across Europe and North America begin to report bizarre electrical phenomena. In London's General Post Office, operators hear sharp crackles and see arcs of blue-white light leaping from the keys. In St. Louis, a clerk watches a sudden surge arc across the metal of his telegraph instrument, the sound like distant fireworks. Entire circuits hum with a low, resonant tone, and some lines emit a continuous, high-pitched whine that can be heard from neighboring streets. The most astonishing detail emerges in the next hour. Messages continue to flow even after the batteries that normally power the telegraph are disconnected. In Boston, a telegraph operator, after turning off his battery, rests his hand on the key and watches the needle swing wildly, driven solely by the geomagnetically induced current coursing through the long copper wires. He reports that a full Morse message can be sent in a fraction of the usual time, the signal riding the invisible wave of the solar storm. Across the channel, an employee at the Royal Observatory notes that he can transmit a dispatch to the Royal Navy in seconds, a feat that would normally require several minutes of careful keying. The storm has turned the world's nascent electric network into a giant antenna, harvesting the sun's energy directly. News of the disruption spreads quickly. Newspapers in London, Paris, New York, and Boston publish front-page sketches of the aurora and detailed accounts of telegraph lines that sparked, smoked, and even melted. Within days, scientific societies scramble to interpret the phenomenon. Carrington submits a paper to the Royal Astronomical Society describing his white light flare and proposing that a great eruption on the Sun had expelled a mass of particles that struck Earth's magnetic field. While his hypothesis is radical, it finds a receptive audience among a handful of physicists who have begun to consider the Earth as an electrical body. Contemporary scientists, including James Clerk Maxwell, mention the event in correspondence, noting that the magnetic disturbances suggest a direct solar influence, though they stop short of endorsing a full theory. Railway signaling, which relies on telegraph circuits, suffers as well. In the United Kingdom, several lines experience false signals, causing trains to halt unexpectedly. Near Manchester, a signal failure forces a passenger train to stop just before a junction, narrowly avoiding a collision with a freight train that is unaware of the halt. In the United States, Western Union reports that portions of its network are completely offline for several hours, forcing businesses to revert to couriers on horseback. The economic ripple is palpable. Stock exchanges experience delayed price reporting, and merchants lament the loss of rapid communication that had become essential for trade. Midway through the narrative, a modern revelation reshapes our understanding. Space-based observations, begun in the late 20th century, allow scientists to reconstruct the event as the first recorded instance of a coronal mass ejection, CME, striking Earth. By measuring the speed of plasma clouds from later storms and applying those models retroactively, researchers estimate that the CME traveled the 93 million-mile distance in roughly 17 to 18 hours, explaining why the aurora appeared many hours after the solar flare, a timing that puzzled 19th century observers. The CME's impact compressed Earth's magnetosphere, inducing intense electric currents in long conductors, a process now termed geomagnetically induced currents, GICs. In other words, the telegraph lines behaved like giant receivers, channeling the sun's energy directly into the Earth's electrical infrastructure. Armed with this hindsight, engineers and policymakers adopt the Carrington event as the benchmark for worst-case space weather scenarios. In the 1980s, a powerful geomagnetic storm, often called the March 1989 storm, strikes North America, causing a 9-hour blackout in Quebec. Scientists compare its intensity to Carrington's, concluding that the 1859 storm was at least an order of magnitude stronger. Modern power grids, with their high-voltage transformers and extensive transmission lines, are far more vulnerable to GICs. Simulations suggest that a storm of Carrington magnitude today could overload transformers, trigger cascading failures, and plunge continents into darkness for weeks. Satellite constellations, GPS networks, and airline communications would also suffer, echoing the telegraph disruptions of 1859 on a global, digital scale. The mystery endures. Why has a storm of comparable magnitude not been recorded since? Solar cycles, lasting roughly 11 years, produce flares of varying strength, but the Sun appears to have a superflare ceiling that is rarely breached. Some researchers argue that the Carrington flare was a statistical outlier, a tail event in the distribution of solar activity. Others suggest that earlier, pre-telegraph societies may have experienced similar storms, but the lack of a global communication network left them undocumented. Recent analyses of ice cores and tree rings have identified spikes in carbon-14 and beryllium-10 isotopes that could correspond to massive solar proton events, hinting that the Sun may have unleashed comparable eruptions centuries ago. The 774775 AD event, for example, shows a carbon-14 increase of about 1.2%, a magnitude that some scientists link to a solar superflare. In the 21st century, the legacy of that September night is woven into every piece of critical infrastructure. Satellites now monitor solar activity in real time, providing advance warnings of incoming CMEs minutes before they strike. Power utilities install protective relays, series capacitors, and neutral grounding schemes designed to block GICs, and governments develop emergency response plans that include preemptively shutting down vulnerable sections of the grid. The U.S. National Oceanic and Atmospheric Administration runs the Space Weather Prediction Center, which issues alerts ranging from G1, minor storm, to G5, extreme storm. Yet the fundamental vulnerability remains: a sudden, massive influx of solar energy can still induce currents that overwhelm even the most robust systems. Scientists continue to refine the probability of another Carrington-scale event. A 2012 study in space weather estimated roughly a 12% chance of a storm of similar strength occurring in the next decade, while a 2020 review placed the odds at about 1 in 100 years. Observations from the Kepler Space Telescope have revealed that Sun-like stars can produce superflares many times larger than any recorded on our own star, suggesting that the Sun's magnetic engine is capable of far greater outbursts than the historical record alone shows. The lingering question that haunts researchers, engineers, and policymakers alike is not if another Carrington-scale storm will occur, but when. As we watch the auroras dance over the polar skies each year, we are reminded that the Sun, our life-giving star, can also become a cosmic wild card. Will the modern world, with its delicate web of electricity and data, be ready to survive the next solar blast, or will we once again hear the hum of our creation sputter into silence?